Ja.
En is die scherp?
Ja, die heb ik scherp gezet.
Ja, oké.
Wel een beetje draaien nog. Ja, juist. Ik wist niet dat er een kantje ging staan.
Ja, zo is die wat beter ingezoomd. Hè? En je kan hem ook, ik ga toch niet hier staan.
Nee.
Nog ietsje draaien. Ja, zo.
Ik kan bewegen om die schroefjes los te halen. Zoiets. Iets uitzoomen zijn. Ik moet je twee uitschieten. Op een derde moet je zitten toch? Voor de zon. David Lynch moet geloof ik.
Je hoeft dit stuk hier niet te doen hoor.
Nee?
Nee, volgens mij niet. Wat heb ik daar nou aan? Hè?
Moet ik meer inzoomen dan?
Nee joh, gewoon even draaien.
Ja.
Ja, pitch, roll, yaw, weet je?
Ja,
Hè? Roll, pitch, yaw. Hè?
Een ja hebben.
Ja, je moet een yaw hebben.
Ja, dat is goed. Nu scherp? Ja.
Ik check nou eventjes, is hij nog steeds echt scherp?
Ja.
Met de gele lijntjes en alles?
Ja, hij pakt de letters lezen.
Ah ja, oké. Huh? Want je bent zo lekker bezig. Hè? Zijn we nou dit allemaal aan het opnemen? Hè?
Ja.
Oké.
Gewoon de bloopers.
Over de bloopers van de outtakes. Huh? Alright, so we're going to continue, and this is slightly different than what I promised you. So I was promising to get back to the pricing, and in fact we're just not going to make that. But I got a bunch of questions. I also got a bunch of compliments, and the compliment ended up being a bad one because they said how well I did this Lee group without getting into details, but there were some details that I just hadn't addressed that were important. So I wanted to correct those things. And then what I also wanted to do was just go on one more lecture about manifolds and different types of manifolds that are really useful for economic analysis. And there's a bunch of stuff they do with production functions, production possibility frontiers, all the basic economics. And they put themselves in some weird space and they draw things. Maybe I shouldn't say weird space, but in some space. And then they draw things just on paper. And I wanted to do a geometric treatment of those things. So you get a good feel for how you take a standard economic problem and then translate it. All right, so I'm going to pull this thing up. So we got through all of this. I don't want to do this anymore. We went through this. And remember, then you just have a one-dimensional commodity, okay? You still, just because that's a one-dimensional thing, still you still have some choices, okay? And one of the choices is what metric, how are you going to measure, the size of your flow, all right? Your quantity demanded. How do you measure that, right? Do you measure that just linearly with a regular Euclidean scale, that you put your this is what you would think, huh? But you can also measure it logarithmically. This is what's sometimes called a hyperbolic metric. Okay. And then you would use a log scale. And economists do this a lot with growth, economic growth, population growth. They assume that this is a unit speed. You do it also in the stock market, when you look at certain prices or something, okay, money flows, returns, you would use this metric, all right? So this emphasis on spaces, and you see, what you have to see is when we have this manifold, really it doesn't have much structure at all. All we know is that 2 points are close, okay? And that we can take a sort of a differential here. All right, that allows us to define this flow, okay? But that's all. We don't know whether this, how long this vector is, or whether we can square these and add this. We don't know anything yet, right? We just have this basic setup. And the approach is very different than the usual way we do economic engineering or economics, is we start with this minimum space, and then we slowly start adding layer upon layer of extra structure. And every time we add a layer of structure, we need to motivate it, you know? When we do physics, we have to motivate from a physical point of view why this is allowed, why you can take a distance, square it, and add it to another distance squared, all right? And if we do it economically, we have to do the same thing. Why we can take apples, square them, and add them to pears and square them, okay? Doesn't seem to be allowed, and there are a lot of folk wisdom that you shouldn't do that, all right? So, but nevertheless, there are certain structures that you can identify that economists typically assume kind of implicitly, and I wanted to unravel that, okay? We'll give you a lot of, so remember this. So this is one way of defining manifolds, you know. So here it was defined by the fact that land just doesn't increase or decrease, okay? So you sit on a one-dimensional manifold. This is a contract. This is also a contract. When it gets enforced, you get weird manifolds, okay? And then we're also able to put a metric on these manifolds, okay? So we can measure what the demand is, and we can talk about when demand is constant, okay? So in this metric here, you will see that the demand here is constant in the usual sense, but here it's not constant in the usual sense, because if it were here and you end up here, you say, well, hey, it's not constant, I rotate it, right? Huh? But on this manifold, in this metric, this is constant, so you just carry it along, okay? All right? Huh? Sometimes in Riemannian geometry, that's called a connection. Right? So this is a problem. Like, what is going in a straight line? You know, now, is that really a straight line, what you think? Or is that just going along a great circle when you're walking on the Earth, right? Or flying your airplane around the Earth? You go to a great circle, so it's not straight at all. But it is straight in that metric for that manifold. All right? Huh? And then we also saw a little bit like, if you have a metric, there's always a group of transformation that leaves it invariant, right? So you can like turn it, and then still this thing will be, huh? Okay. And then we saw the use of the exponential map that links the two concepts, okay? Right? So I wanted to go through two like big kind of applications. Here's what I want to achieve. I'm not quite sure why this clicking is not working. Maybe it's just slow. Yeah, it was slow. So I first want to go through something called production possibility frontiers and talk about the projective plane. Then I want to talk about isoquants. This is not going to be as long. Then I want to start thinking about firms. And I want to show you that they look like rigid bodies, you know. You all know rigid body motion. So that's a cool thing. I first want to do it in 2 dimensions. Then work it out when you have a separate frames, okay? So we can think of it from different perspectives. And then I want to do it in 3D. This thing is where I want to end. I'm not going to go through the nitty-gritty details, but I want to give you the ideas of where this thing becomes really important and a non-commutative group. So when you first do in your business, first sell eggs and then sell something else, it's not the same as turning it some around, all right? Yeah? So let's get started. Now, the production possibility frontier is a favorite thing in economics. I probably should have gotten the Wikipedia page of it, but you can look that up. And I don't know, are you guys familiar with this concept? Have you ever heard of it? So it's really old, and they use it in economic text to illustrate a lot of economic concepts. And there's a famous example about guns and butter. So this is a 3D plot. Let me first draw the 2D plot like you would see it in, actually maybe I can, let me just draw it here, a 2D plot like you would see it in Wikipedia, all right? So you have this society, and it can, I guess this came out of World War II. It was even Goering who was talking about it, you know. And there was this whole thing about, okay, if you have an economy, you have certain resources, and what are you going to do with these resources? Are you going to make guns, huh? You know, to shoot people with? Or are you going to make butter, huh, to feed people with? Okay? Now, given the resources that you have, your factories, your working population, maybe you could produce so much butter. And if you apply all these resources to producing wartime production, you can produce that many guns, right? I just scaled this arbitrarily, right? And then you can go and see different types of mixtures, okay? Now the idea is that these mixtures will go something like this, you know now? So if you want to produce, if you're producing a lot of guns and butter, and you want to produce some guns, you know, you can make a movement like this, and you can produce some, and it's not going to affect your production of butter too much, okay? But at a certain point, you have these diminishing returns, and it starts affecting it, and then somehow you come over there, right? Huh? So this is the idea of a production possibility frontier. So efficient use of the resources puts you here at an efficient, that's what I call an efficient allocation, all right? Huh? And this is another efficient allocation. So if you're producing this, it's inefficient, and this one is infeasible, I believe they say. I don't know what the terminology actually is. We can't do it, all right? That's the idea. And then what they will do is they say, all right, now what's your budget, okay? Now suppose the price of guns is this, and the price of butter is that. Then you would draw some line, huh? And that's your budget line, okay? So this is your production possibility frontier, and this is your budget line, huh? And then you'll say, well, this is the best point. Well, given my budget, all right, huh? I can produce, this is the most efficient point, okay? And they go and they analyze this. And they call this slope here the marginal rate of transformation, you know, because that's the rate at which you can transform production of butter into that of guns, etc. All right? Huh? This is called an isocost, I believe. You know, it's a device that is a very popular device to show. All right? Now, how are we going to plot this as a more geometric, as a manifold? All right? Okay. So they talk also about this. Maybe I should add that. So if you have your production possibility frontier, then these are your resources. But if you increase your resources, you know, you would push this thing out. Okay? You see? That's called expansion, and then you may have an expansion path, and then you can go out. All right? Huh? Right? Okay? Simple. So, okay, so now let's get, how are we going to attack this if we want to do a geometry, all right? So the first thing to do is to get yourself in the right space. So we first have to count, so suppose there's only one agent, you know, it's the economy itself, or I don't know, right? So we first have to, then we have to count the number of goods. How many goods do we have, right? How many different queues? Well, there's guns, right? There's butter, okay? Any more? No, well, I would say, yeah, there are these resources. You got all these capital goods, right? Huh? Okay. So what you want to do is you want to keep track of that, because otherwise, how are you going to say I increase my resources? So you see what goes wrong with this picture, you forgot about something, right? Huh? In your effort to go, you know, to say no. You forgot about the resources. Now, these resources are just one variable. That's the way they think about it. Okay, whatever. Huh? But you still have this one capital good. These are your resources. You know, now they all throw together. All right? Huh? And then you have these two goods. So I would say the space is three-dimensional. All right? You guys agree? Huh? That's just the setup. So here I am. I plotted this three-dimensional space. So I guess the guns axis is right here. It was dropped out. Huh? Okay. I got guns and butter, so I took this thing and I turned it like that. And I plotted the resources going up like that. Okay? Okay? Now this gives me a nice way to analyze these. So now I can see all these different production possibility frontiers. I can put them all in one shape. Okay? So let's say the resources here are 1. So this was resources 1, and then this is it. Okay? So what I do is I go to point 1 here. Okay? This is R is 1. And then to see how much butter and how many guns you can produce, well, I'll have to get a plane that is parallel to the guns and butter plane, but then shift it up 1. Okay? Clear? So if I start producing butter, I'll be going this way. If I produce guns, I'll be going that way, right? Huh? And then in a year, I would have gone this far, but had I gone in another direction, I would have been there. So I will draw the circle right on that higher level plane, right? Huh? Okay? That's what I would do. Now, if I had more resources, I would draw the plane over here. Boom. Huh? And then just draw it a little closer down. And then here, that point, efficient allocation would end up over there, right? Huh? So to all efficient allocations, independent of where you are, right? You can now do, but you draw a ray from 0 and you go up, and you see where it punctures every resource plane, okay? And there you get the point that belongs to that efficient allocation, okay? And if I put them all together, I'm going to get a cone. All right, you see that? Huh? And then if I slice a cone by a plane, I get what is called a conic section, because you section it by a cone. And because I do it here orthogonally, I get a circle, right? Huh? So the way we now view this production possibility frontier is by conic section, okay? So this is what you need to see. So we have to add this dimension, but now we get a lot of structure in this space, okay? This is just not some old space. These rays are special, for instance, because they give us an allocation. A particular allocation is given by this ray, huh? Okay? Efficient allocation, that is. Now, what is this ray saying? You see, it's saying that whatever your allocation is, you could bring it back to this point. You can project everything to this point, and that's sort of a generic allocation, you know, by R is 1. Okay? Now, a space like that is called a projective space. And why is it called a projective space? Well, because you're projecting, right? Huh? And this is a little bit how our eye works. Huh? That's why they're cool. So if you imagine yourself sitting here and looking up, and this is your drawing canvas. So this is your canvas, huh? On which you're drawing. And this is basically what you do, right? So you have this light ray coming in, right? And it's going to hit or going. You can think of it going out. So light rays actually don't travel that much. Huh? So then they're going to hit a point, and that point you put in that canvas, but you don't know where that point is. Is it here? Is it here? Is it here? You know, all the stars will be, you know, if you take a photograph, all the stars will be aligned on that plane. Okay? Okay, so this is called a projective space, and this particular one is called the real projective plane, RP2, in 2 dimensions. Okay? It's an interesting space, because every point on the real projective plane corresponds to a line in the ambient 3 space. Okay? You see that, right? Huh? And this marginal rate of transformation is a line, and that will be represented by a plane, because you will take a plane and pull it out, and it will slice the projective plane, huh? By a line, okay? Okay? So points are lines, and lines become planes. So we reduce the dimension. It's very, very natural. This is what they use for vision. You know, these guys doing vision here in the department, that's what they use. And then what you do is, your set of coordinates you use are called homogeneous coordinates. So you take guns and butter, and your resources, and this means they are in the same proportion. So this point is the same as this point. I just divide by the resources, okay? It's interesting because the only point that is not there, what happens when this is 0, right? Huh? Then you can't really divide by 0, huh? So that point is special, right? So that's when you have no resources, okay? So if you're then producing with no resources, you're out at infinity, huh? Okay. So we call that the point at infinity. So if you put the 0, then this is the point infinity, or the line at infinity. So every allocation, you're out at infinity. So you can imagine if your eye is looking, and then to find a point further, it has to look there, and finally it has to look horizontal, and then you look at the horizon, okay? And then that's the point of infinity. Now this is an interesting space. It was figured out in the Renaissance by these Renaissance artists, I think in Italy. They didn't get this in the Middle Ages. When they made pictures, you see, even if you go to Van Eyck or something, it looks a little bit plastered on. And then finally, these painters in Italy, I think it's Brunelleschi and those, right? They figured out that you have these vanishing points, that when the eye goes like this, the point goes out in infinity like that. All right? Huh? So you have parallel lines here. They start meeting in infinity, right? Because normally in the Euclidean plane, parallel lines like this, but if you go to the projective plane, you'll see that this is a railroad track. They'll meet at this point at infinity here. So you have a whole line, extra line at infinity. That's when you're infinitely many. You're production efficient with your resources. Because you have no resources, you're still producing. Okay. So this is a very interesting space. It's one of the first, I would say, non-trivial spaces that people discovered. Now projective space, and you need it for perspective theory. So you got to appreciate that looking at something like production possibility frontiers, things that have an expansion like that, it's very good to do that in a projective space. So people start drawing on this canvas, and you would think, if you go to the picture, you would think it's two-dimensional, but really it isn't. It's a three-dimensional situation that's projected on a two-dimensional canvas. Very similar to the eye, an artist, or the camera does it, right? So you take a three-dimensional reality, project it on two dimensions, and then the expansion becomes, a blowing up of the figure, or contraction becomes, the farther away it gets smaller, but it's the same thing, okay? They're really cool because you can draw this circle and you homogenize it, right? So if you so this is the equation for a circle in the projective plane. So you got 3 coordinates. So everything is a quadratic here, okay? Yeah? And a line, you do it like this. In this case, this thing is 0, right? That's all. So it's this plane. And it's a kind of calculus that goes inside of your camera. I don't know if anybody of you knows this, how they do this with homogeneous coordinates. These robotics guys, they do this all the time, or whatever. Now, on the projective plane, that's just a manifold, okay? So, you can say, this is 2D manifold, but look, be careful, right? Look at the structure, right? So there's an invariance group. It's actually called the projective group, or the perspective group in 2D, right? So those are the deformations you can do to still get the same picture, right? So you'll see there's scaling in there. You'll get weird rotations and skewing, all kinds of stuff, okay? So you can look at a metric that's invariant under that. That is probably not what you want to do. What you want to do is get a metric that is consistent with your production possibility frontier. Now this is a circle, okay? So the usual metric, the Euclidean metric for the length of the circle here would be the one you want to use, right? Now, they talk about an expansion. So the circle gets twice as big. What does that really mean? Now you can just look at the regular Euclidean metric and look when the radius gets twice as big, right? But that's not what they mean. They look at an expansion in terms of percentages. So they would put a logarithmic scale on these rays, right? You know, so the resources are twice as much, or 10% increase in resources. They don't say, huh? Okay, huh? Or a 30% increase. They didn't add 5 to the resources. Economists always work that way because then they can avoid using units, right? Huh? Otherwise, you have to talk about 5 machines adding it. Huh? All right? So they will put a logarithmic metric on the plane. Okay? Are you guys okay with that? Huh? Now, how would you do that? We know how to put it on a line. Now, how would you put it on a plane?
Have like the Cartesian product of 2 logarithmic lines?
Yeah, you could do that. That's not a bad idea, right? So you will take the log of, I mean, it's a very good idea. Huh? This one, and then the log of the butter of this, right? Huh? Okay? Yeah, that will work. Huh? So you take these homogeneous coordinates and you just put logs in front of them. And then you'll see that instead of dividing by the resources, you subtract the resources. So what the log does, it actually turns these homogeneous coordinates into sort of affine coordinates. Like we say, affine coordinates are the ones you just add stuff. All right? Huh? Okay. That's not a bad idea. Typically what people do is something even easier. So you think of this as the complex plane. Okay? And why do I think of it as the complex plane? I'll tell you why. Because I see this circle here. And I know in this complex plane, a circle is easy. That's the circle, right? Or if I want to walk around and reallocate, I can do something like this, right? That's a reallocation rate. Huh? You know, where omega is just the rate at which I'm going and t is time, okay? Huh? All right? Huh? So if I take the log of that, I'm going to get this thing. Right? So put it over here. So that's the imaginary part. Huh? Now, how about the expansion? Well, that's easy too, because I do E, and now suppose I expand at a rate sigma times t, right? So this is the rate at which I'm expanding, sigma, all right? Huh? So I'll have e to the et, and I multiply it, right? Huh? Or, huh? I can also add them here. And this is equal to e to the sigma plus I omega times t, right? So by taking, if you think of this as the complex plane, by taking the complex log, you straighten this whole thing out, right? So here will be the angle, and here will be the expansion factor. That's the point of the complex log, okay? To straighten out the complex plane. Because you guys all know this formula here, right? Huh? I mean, we use it in Laplace transforms, where this is then the damping, and this is the angular frequency, you see? So all we're doing there is we're taking this complicated thing and then flipping it into a linear scale, all right? This is the linear scale for the underlying signal. That's what the angles do. Okay? That's how you see how the exponential map, really it takes something, a rate, which is just a vector, a linear vector that you can just add, and if you exponentiate that, you go into the group, right? Huh? So if I exponentiate this, I'm going to do a rate of reallocation and at the same time a rate of expansion, something complicated, but here it will be just a straight line. All right? So here it's a straight line. Huh? Okay, this is omega. Huh? And this one here is sigma, huh? The rate. And here you get your, I don't know what you're doing, right? Huh? Okay? They call this the reallocation rate and the expansion rate, these two things. Okay? What I want you to see is that it's just putting, now a metric, the regular Euclidean metric, but it's really the action of what you would call the complex multiplicative group, okay? So we have the real multiplicative group. That's just a regular real growth, okay? And this is sort of a complex growth, where you're not only growing the radius, but you're also growing the turn. And the log of the turn of the rotation is the angle, right? Huh? You see? Now, had you not looked at it from this manifold point of view, you probably would never have thought of that you could use the complex log and just throw the reallocation and the expansion together, right? But you guys know this. Multiplying by a complex number not only amplifies the number, expands it, but also rotates it, right? Huh? Okay. It's a cross of two groups. It's the group of the expansion group or dilation group and the rotation group. They're in this, if you look at the cross of these two groups, you get the complex multiplicative group. There's some, Tristan Needham has a great book on it. He calls it an ampli twist. So you amplify and you twist at the same time. All right? Huh? That's what the complex log does. That's why it's so useful in a Laplace transform for damned harmonic operators, because it amplifies, it doesn't, it really contracts, there's a minus sign, okay, whoopity-doo, we can deal with that, right, minus sigma, and then it evolves, right, there's also a minus sign, so it goes into the clockwise direction, all right, huh? Okay, thinking geometrically just cleans this up. Have I convinced you about this, huh?
Question on the MRT. I have forgotten what it stands for.
The marginal rate of transformation.
Okay, and is that the tangent really to the BPF?
Yeah, so that's what I said, right? When we have this. Yeah. So you can look at this as the MRT, it's a tangent, right? Huh? So it tells you what is the marginal rate at which you can transform your productive resources from guns to butter, okay? It's called the marginal rate of transformation. And they use these kind of graphs to show you the significance of that. So it's a line, right? Eh? And the rate you're transforming, that is this thing, okay? And the rate you're expanding, and this is what they would call so this is, if you look at their analysis, this will be an expansion path, and this will be sort of marginal rate of transformation, right? Okay. And then when they look at a real path, it may go something like this, huh? All right, huh? And that's what they say will be the real expansion path, all right? Now what we are doing, if you look at this from a geometric point of view, you say this expansion is a vector here, which I'll just call is a real vector. Okay, why is it real? Because it's in the same direction as the radius. I mean, we're doing nothing to the number. We're leaving this the same. Okay, we're not changing this radial line. That's how we're expanding. And then the reallocation, we say we are 90 degrees rotated. Okay, so I got to put an I in front of that. That gives me the 90-degree rotation, and then it has its own rate. And that also happens during t, right? Huh? Okay, so I have a vector here, and this vector is sigma plus I omega times t, okay? And then I want to go out in the Lie group, right? Huh? Okay, now I want to, well, you don't even go in the Lie group, you're just kind of following your vector field. So well, how do I do that? Well, I use the exponential map, right? I take the exponent of this thing, huh? And there you have it. And if I want to go backwards, well, let's go, this is the vector pointing the other way, that's a contraction, and I'll have a minus sign. Huh? Here, okay?
So that because of the structure that this particular problem has, you can instead of looking at the path of it on the surface of this cone, let's say if you're looking
Yes.
at just the efficient allocation,
Right.
you can, because it's isomorphic, this whole manifold,
Yes.
to the complex
So you
plane.
project it to the complex plane.
Yeah,
So you
can
project it to the
just-
real projective plane. You identify that with the complex plane.
Yeah, exactly.
That's a little bit of a difficult issue because what is the complex plane? Doesn't have an end? No. Does it have a?
But neither does the
It
surface
does.
of the-
This one does. This one does because you remember the line at infinity at 0.
Yeah, true.
So this one happens to. So it's not the same as the Euclidean plane. The Euclidean plane has no end. This thing has an end, and that's the horizon. So it's like you're on Earth and you're looking. There's an end. That's the horizon. Now the Earth is round, so the horizon should be a little bit higher. But nevertheless, if you were standing on a plane, right, and a plane would extend indefinitely, you wouldn't see indefinitely. You would
Right,
see
right.
a horizon.
That's why if you wanted to get to that point with transformation, you have to have like minus infinite expansion.
Yeah.
Yeah.
Sure. That's not a problem. There's still a horizon. That point is still there. You
Yeah, but
see,
it's
that's what you got to see. So this is a plane plus one line at infinity that's way out there, right? A little bit like what do you call a pole plot, right? Don't they have a line at infinity? I think they have a point at infinity, but you can also do that. One point at infinity. But here, there's a line at infinity, all right? So you know when you do that integration, go out and woo, you go around, okay, And that corresponds to when this is 0, okay? That's a point here, but that corresponds to a line at infinity, okay? All the directions that you see the horizon. So there's a whole line. So what is the real projective plane? It is the same as the Euclidean plane plus an horizon, right? All around you, okay? Some subtleties, you know. And normally as engineers, you just fill those in and you go, okay, it's the same. But that's right. So you're sitting in this big space. The projective nature of the space allows you to reflect it on one canvas. And then because you're imposed this cone as being the structure, so what you did is you impose a couple of things. You know what a point is, those are the rays. That comes from your projective plane. Then you know what a line is, that's just MIT. That's those planes going through the origins. Then you know what a circle is, that's a cone. So then you got enough. So this cone, this gives you the reason to use complex coordinates because you can use the angle, right?
So if you want to describe assuming you're always going to be on your PBF or
Yes.
corner frontier, you're going to move on the surface of this
Yes,
cone, right?
that's right.
And then instead of having to look at this plane that's tangent to
Right.
it, and which is also in 3D, you can put it all on
Yeah.
the complex plane. And you can see it.
Exactly,
But it's
exactly.
only because we have the structure that you
Yes, that makes sense. And that this thing can be called the expansion rate, and this as the economic is the reallocation rate. You can take some other thing where there's some weird structure, then what has this got to do with anything? Nothing, right? Huh? See? Huh? So I did this whole mapping, and I ended in something that just has economic significance. Why? Because it reflects the structure we put on here, all right? And how did I do this? Well, I looked at what they're doing. I read the little article, and I went, okay, now how do we translate that into some serious geometry? So we know what are just choices and what are, I mean, you're asking a really good question, and you're completely right. I accept that in my enthusiasm, I'm adding all the other stuff, you see, to make you fully get it. So yeah. So I promised you start off with this amorphous space, and then you look at a problem, and then you start recognizing what structure they are assuming, and then you try to put it on. And then you take a coordinate system that respects the structure. And that gives you, then everything looks easy, okay? Then everything looks easy, and then you can solve the problem. Now, in most engineering problems, that's already done for you. So you have this pendulum, you go, oh, I'm going to take an angle, right? Okay, But here, that's not done for you. So you got to kind of get serious about this. But you've done it so many times in other problems that you immediately recognize what's going on here, okay? You've used the complex log so often, you know, So if you think of this as a point z, you take the complex log of z, what are you going to get? You're going to get the log of your z plus I theta, right? Huh? Okay. Simple. I mean, what does that do? That just this actually is also an angle, right? Huh? It's just an expansion rate, sort of a weird angle, right? It's how much you expand it out per unit of where you were. You know, one way of looking at an angle is what is it, right? So an angle is just what you do when you have a circle. So you're here and you're expanding out, but you happen to be expanding out orthogonal, right? So you know that you have a rate of I theta, like that, huh? Okay. But what if it's not orthogonal? Then you're just expanding out along the real axis, and just take this thing out, right? Huh? Okay. Huh? Okay. Huh? That's all you're doing. So this is also a sort. An expansion is also a sort of an angle, right? Huh? You're dividing some change by the radius, except the change is in the same direction as the radius. So that's what the complex log does. It has the sigma part gives you the so this log z, that is equal to sigma t, right? Huh? Okay. Well, that's all it does. It's sort of an angle also. That's what we call it. We would call it a rate. Huh? Okay.
I think I can incorporate this in my thesis as well. Very
Sure, sure. Yeah.
My budget function is how much people distribute their resources over the goods of rental services and other services and owner-occupied housing services. Three
Right. Yeah.
axes.
Yeah.
It also expands up with the stable growth path. So I think I can.
Yeah, so you can do this, and it really helps to clarify your thinking. And then in the end, you'll realize, oh, nobody's waiting for that. Just give you the solution, right? But you know, this is research, and it's good to get the reasoning right. You know, huh? So yeah, huh? Look, normally, you know, all this stuff comes falling out of midair, you know, huh? So from there, so I put all the structure in there. So you have the Euclidean metric, and you put it on everything, right? And why, right? So you have, econometricians do this, so they have one variable here, x, and here another y, and they got a point cloud, and they do a least squares, right? Now, what does that mean? You take a line and you start looking at the square distance, right? Huh? Something like that. I don't know how they do it, but that's what you do, right? Huh? So why are you squaring this, right? Why are you adding squares? Huh? Why not take a log here, right? You know? Huh? So you see that something that looks innocuous like that, there's already a very strong assumption that the metric that you have on the blackboard is precisely the metric of the problem. And just because this blackboard is in Euclidean space, well, you think it is, right? That doesn't mean your problem is in Euclidean space, you know? Just because it looks close, that doesn't mean it is close, you know? What do you mean by close? You see, you got to define your metric. Huh? Okay, huh? You can deform anything. And you know that. You look at the map of the world, you got to look at the legend. What's the metric here? What are we measuring? Is the North Pole really that big, infinitely big? No, of course not. Right? The metric is all screwed up. All right? Okay? That's one of the many things I have against least squares analysis. Like, why the square? Huh? All right? Huh? You know? Oh, it makes it easy? Well, other things are easy too. Huh? Why not just sum it? That's easy too. Uh-huh. Yeah, but then it doesn't converge. Okay? Yeah, it's fun, you know, after these lectures, go look it up, homogeneous coordinates and these barycentric coordinates. It's kind of fun, projective space. Huh? And it's very natural, and I think it's natural because of the way our eye works, right? The eye in our brains is this built in, right? We can easily parse this out, huh? 3 seconds. Huh? We have a decoder for projective space built in. You can do other things. Instead of a flat canvas, you can put like a round canvas, right? So you can project it on a ball. Huh? So you put a ball around here, right? Huh? And then you go out. Huh? Sphere, not a ball, a sphere. So you know, if you go to Panorama Mesdag, huh? I believe they have that, right? Huh? So instead of projecting it on a flat plane, you project it out on a sphere. Huh? You can do that too. You get a different picture. Huh? It can be cool. That's what we do when we look at the stars in the sky, right? So if you see these pictures, you imagine there's a big celestial sphere, it's called, I believe, right? Huh? Yeah, the celestial sphere. Huh? And hemelse gewelf of so in Dutch. Huh? Something like that. Hmm? Yeah, so you don't imagine a plane. You know, now you imagine on this Earth, and then there's this bigger kind of sphere around you, and you project all the stars on this one sphere, and then you start drawing, you know, some kind of baking pan, you know, and you call that the Big Bear, and you have a smaller baking pan. You know, you have these pictures, but you know, you don't know which star is further or which is close by. I have no idea. It's irrelevant for the description of all those you know, pictures. Huh? Okay. Orion's belt. You know, belt. You can also graph it on hyperbola. Huh? Where you get other things, hyperbolic geometry. Huh? Well, maybe we'll get to it someday. But I also want to cool down about this because you can go really. It's really interesting. Huh? And some very cool math was done, especially in the 19th century, to understand all these spaces, you know? So what happens when you project on a sphere? So there you get Riemannian geometry, you know, and then on a hyperbola you can get hyperboloid, you get, you know, this hyperbolic geometry, Lobachevsky, which is, and you use that for relativity. I projected on these spheres in Minkowski space, whatever. What we're doing is using this for economics, right? So we're gonna like cool down a little bit, but I don't want to cool down too much. You know, it's just cool. You got it. Huh? It's part of your education. All right. Then this one was a long one. Any further questions? Here's a shorter one. Here they have these things called isoquants. You can look that up too. In the previous one, we had one form of capital, we just called it the resources, and two products. When economists do production theory, it's the opposite. They have two forms of capital, physical capital, K, they call it, and non-physical, human capital, they call that L for labor, okay? And they make one product that they call that output. Now usually these are stock variables, so there's a real amount of physical in this one, but this is a flow variable, this Y, output is per unit of time. So what I'm plotting here is of course the time integral of this, okay? So a vector, output, so this is output, huh? I got it here, is a vector here, right? Huh? At this point, okay? Now, what they assume is that, you know, you can wiggle how much capital, how many machines you have and how many laborers you have in various ways, and then you can collect the ways in which, wherein you have the same amount of output, okay? And these things, they follow something called a Cobb-Douglas function. So here I drew one. I think this is a simple hyperbola where this is one, and this one is one. That's because it's easy to program, all right, in ticks, okay? But it already shows you something that if you've only got labor running around, you're not going to produce anything. You need some machines. And if you only have machines and nobody to man those machines, you're not going to produce anything either. So these things, they asymptote, of course. Huh? and in the middle is probably your best bet. Yeah, right. So you have some kind of optimal combination. Huh? Now what they will do again, they'll have some kind of iso-cost curve, you know. So they'll say, oh, here I drew it here. They'll say, all right, there's a fixed price for machines, a fixed price for labor, and then if I combine that, then this is what I can afford. So this is my best point. Yaga, yaga, yaga. All right. Now we don't talk like that, right? We don't have fixed prices. We have dynamic prices. So it's nice to know that this is an iso-cost curve. Huh? This line is also called the marginal rate of technical substitution, I believe. Okay, because they can use either technology, and they can substitute one technology for another. So they will call this the marginal rate for, huh? All right. Okay. We can look. This is called production theory. All right. So what's interesting is they give a flow variable here, right? So this is like a velocity, right? As a function of these two position variables. Okay. There's a factor here that they call the productivity. Huh? The factor, this is called a factor productivity, and these are called factors. Huh? Factors of production. Huh? And then this thing is the factor productivity. They think of production needing several factors, all right? And then they do these kind of things. They like to have exponents here because they like to measure elasticities in percentages. So if you take the logs of this, of course, this thing becomes a, huh? All right? Huh? Economists don't do units. Oh, also, economists are very, very easy about the distinction between flow variables and stock variables. So this thing is, of course, in the tangent space, and these ones are in the base space, the configuration space. All right? Huh? But they don't worry themselves about that. Huh? They don't worry too much about units and that kind of stuff. So for us, this axis, you have to integrate it out to get the total product that you made. All right? Now, what you may assume is that you just have a fixed amount of resources, and then this is just the isoquant that applies to your economy. So you can produce here, so you'll get this sheet going up, right, as your manifold. Okay? And then if you want to have constant output, well, you'll see you have some kind of metric that's really easy. It's just measures this distance, right? So this is blue because it's in the tangent plane. And then in the tangent plane is where you measure the metric. So it's a small displacement you measure, okay? So it's just constant, okay? And I guess you could do a projective thing. You could like going through here, and you can put some other isoquants, I don't know. Huh? You could do that, huh? You'll have to be careful that you use a different, yeah, well, whatever, okay? This is the basis for these growth models they have, the solo growth model. I don't know if anybody's heard of that. Huh? Production functions. Huh? Never? Huh? You have, huh? Yeah. You have. Huh?
And Behrens uses the solo growth in this.
Yeah, he uses this in one of them. Huh? Yeah. This is the basis of the solo growth model. So economic growth, they'll measure like this. And they have two things, and then there's, then somebody measured that this was 0.74 for the U.S. economy some time ago, I think in the 60s or 50s or something, and it seemed to be incredibly stable. So they were convinced this was it. But then came all these technological innovations, and then labor productivity went way up, and it wasn't 0.74 anymore. So they didn't really know what to do, so they added this thing. Okay, huh? And this just corrects for how far you're off. Huh? And this thing is just a function of time. Huh? So every time if you're off, your model is off, you just put a correction factor in front of it. That's what they do. I wouldn't do it that way, but huh? But that's just, don't forget, all I'm doing with this thing is measuring the length of this vector. It's really not so relevant for the description of the manifold, but more for what kind of metric are you placing on it, okay? Huh? All right, huh? Okay, and that they specify it this way. There's books and books and books on this, okay? Huh? So, anyway, that's one reason I like to put it in, so, you know, huh? So you see the space has to be three-dimensional. If this is another thing, not just a constant factor, you got to add that too. I don't even know how you would do that, because how do you measure productivity? What is it? But whatever, huh? Yeah, I can't imagine this being a dimension. You gotta be able to touch it, huh? I don't know. I don't recommend necessarily using these models, but I do recommend looking at them. And if you use something else, at least how does it relate? And huh? You know, huh? Often you can use them, and then there's whatever, you know. And okay. So far for production theory and isoquants. And then I want to talk about, firms, okay? Firms and corporations. That's a big subject. So I have an hour. All right? So let's go back to what we had before. That was this thing. And we're just looking at this single agent, and you have this one asset, and it's amortizing. And we're gonna make it a little bit more interesting. So, all right. Wrong way. Suppose I have a firm, and it has an asset, like land. Here is a firm. It owns this asset. Now, if you're a firm, you can't just say, hey, I got an asset. No, you got to book a liability, okay? So you have to keep your balance sheet. So for every asset you have to do this double entry bookkeeping. So for every asset you have, there is some liability associated with it. So suppose you bought this asset with money you borrowed from the bank, all right? Then you have a liability consisting of your debt to the bank, all right? Okay? But now suppose you bought it of your own money. What is then your liability? Well, the liability is your equity. So you have to imagine this corporation, you throw some money in it or some goods, you know, but then you are the creditor to your own company, all right? They got to pay that out in the end. That's why you get the earnings, all right? Huh? Or you can loan some money to your firm. It's a different legal entity, okay? So then it will be your own equity that you put in there, okay? All right? Huh? So you can either finance this thing with equity or with debt, huh? So suppose you put land in your firm, you can do that. You can put your house in your business. Then the house has a business, but the house at the same time owes you that land that you threw in there, okay? Huh? So these things are, huh? Now this land will give you all this yield, right? Huh? But the other hand, that yield has to be paid out to the person who you owe it to, right? So this thing is doing negative yielding, all right? Huh? Now these are connected, huh? Okay? So that means it looks like a, you know, what is it? Just a rotation, like a seesaw, right? Huh? Now if you want a regular seesaw, it will do something like this, right? But I have taken now land, so it's shearing like that, okay? So there's something strange going on, which is all gets fixed because we use the right complex numbers, okay? So so here was the tip. So you can see this kind of balances out, and we kind of get a couple, huh? Okay? So that's interesting, right? So you see the business just stays fixed here, you put it out, you get this in, and it's just going around, or it's going, or if you are doing this growing stuff, it's going, you know, huh? Okay, huh? Now, if you look at this business, then here, this is what is called your initial capital, okay? Now, if you have a business and you throw some capital in there, that initial capital has to be conserved. So if you make the books later, that land that you put in always has to be there, all right? It can't go somewhere, all right? Huh? So here, how do we express that? Well, this capital here was just simply it was the length of this radius vector. And we all know how to calculate that. If this is the complex plane, you just look at complex and multiply it by the conjugate, right? Take the square root and there you have it, right? How does that work? You know. Why did I put z here? Okay. All right. So how does that work? Well, suppose you have this amortizing loan, then you just do that in the regular way. So you take this, you know, capital I and the product, huh? And then you multiply it by the conjugate. By the way, the conjugate is the same capital, but then the hedge, huh? They go in the inverse. You see that? Huh? You know, it's over here. Huh? This is Z and this is C. Huh? So it looks like a hedge, huh? So the same capital, but then going in the other direction. That's interesting, right? Huh? So you see how they cancel each other out, and if you multiply them, so that's like doing this, you're going to end up on a real number. Huh? Okay? All right? Huh? If you multiply this out, you already know this. You'll just get this, this norm. All right? So this is conserved, right? This is just a constant number, and it doesn't change. Huh? So your initial capital can be measured this way, and it will remain constant. Okay? And the books will remain balanced all the time. Now, how does that work with land? Now, it looks like this is extending, but we have the wrong metric. We need a different metric. Remember, this was a dual plane, right? So when you expand out, you're not going like this. Afterwards, you just stay put, all right? So if I do the same calculation, I'm going to do this times its conjugate. So the conjugate now is just this one. This is if this is z, this is the conjugate direction is the other one, right? And if I multiply that out, I get a k squared. Then this cancels against that, and then I get epsilon x squared, which is epsilon squared times x squared, but epsilon squared is 0, so I get only the k squared. All right? Okay? So the independent of where you are, this thing is the square root of k squared and this k. Huh? All right? Or r, I guess. Huh? K is the variable, r is the value of the variable. Huh? All right? Okay? It's just a funny metric. You wouldn't think so, but it just is. Huh? This is just the way we measure it. Huh? Okay? So here's another thing that you should avoid doing. As soon as you see some lines, don't start calculating distance as if you know what it is, you know? Huh? This is how you define. If this is how you define distance, you got to respect, you know, what metric we're using for the norm. All right? Huh? Okay? Now here you see the same business, but now operating on a compounding kind of thing. And then if you work it out, you know, j squared is 1. So instead of, you know, I squared minus 1, you get minus minus. Here we get minus 1 plus, so we just get this thing. So this is the hyperbolic distance. So this distance is the same as this distance, okay? Because this is how we measure distance. This is how you measure distance in space-time, right? This will be the space part, and this is the time part, or the other way around. Huh? Okay? So fine. Huh? So the same formula applies. It's just fine. You're okay. Huh? You can describe a business this way, you know, and you have those 3 different types. You know, the amortizing, the regular yielding stuff, and the compounding stuff. Okay? And the books will always be in balance, your assets will always be liabilities. You just got to measure it in the right way, right? So the geometry you have to describe the situation has to fit the economic reality. And then initial capital will always be this, all right? Huh? Okay. So I'm trying to give you sort of a metric-free, it's good to develop a metric-free intuition, you know, that you can look at a space and free of the Euclidean metric, you know. Huh? Just kind of imagine that this is just a rotation, but, you know, and this is just the same distance, okay? You just drew it, you know, on something that you thought was the Euclidean plane, but it is not, okay? It is not. This is the problem that people had when they just couldn't believe Einstein's theory because they kept thinking they're in Euclidean space, but they're not, okay? So the space is different, so they need a different geometry, and then all the laws of motion, Newton's laws of motion were correct, they work out as long as you get your tush in the right space, okay? When you're in the wrong space, you get all these weird contraction factors, you know, Lorentz factors, this factors, you know, these, huh? Okay. So get yourself in the right space and then make everything easy. So here is just a Euclidean metric. I don't know, I looked it up. This one really doesn't have a name. Huh? I mean, it's just what you, if you do orthogonal projection, so your sun is like way out, you know, your light source is way out, then it's just your shadow or something, right? Whatever. Or it's the metric you use for infinitesimally small rotations, right? Huh? You know, the cosine is about 1, and the sine is ignorable. Huh? Or doesn't subtract from the cosine is always 1. All right? Huh? Okay? This is sometimes called the Minkowski distance. Excuse me. Because of relativity theory. Minkowski, he translated Einstein's ideas of relativity in terms of geometry. That's what happened. You know, he's the one who drew all those hyperbolas and everything. But Einstein didn't do that. It was later done. And it kind of cleared everything up for everybody. Before it was just seemed weird. And somehow this helps. Okay? So what did we do? We didn't do that much, but we did quite a bit. We start seeing a firm like a rigid body. And a rigid body is more complicated than just one asset. You have at least 2 and you can have more. Okay? And another thing you can do with a rigid body is the center of mass. I mean, here the center of mass will if this is the center of mass, it will stay constant. It won't move. But it doesn't have to, right? Huh? It can do all kinds of strange things. Huh? So that's my penultimate slide. All right. So what happens when you have a more general rigid body? And I'm just going to do the simple one, right? So I'm just going to do this middle one. All right. So again, you have to keep in mind the metric here. This one is equally long as that. You know, you just measure like this, right? Huh? That's all you have to keep in mind. So the thing is probably it should be balanced. I don't know if I figured it out right. Doesn't look very balanced, does it? Huh? But yeah, I screwed up. Huh? But huh? Whatever. Don't worry about it. Huh? So now there's a couple of other things that can happen. Now, suppose this is a rigid body. So it's rigid because these things are not changing. You know, although they're going like this, the distance is remaining the same. Huh? That makes it a rigid body. Huh? So their assets and liabilities all remain the same. It's just the earnings here. We're looking at earnings now. That's huh? So these are expenses, and this is income. Huh? All right. Huh? And I have 2 frames. I have this one frame that I'm going to call the investor frame. That's the spatial frame. And another frame here in the middle that I'm going to call the management frame. I'm going to put that at the center of mass. And I'll tell you why I'm going to do that. All right. Huh? So suppose these things are not going in the same speed, then you can add up all these velocities to get the center of mass velocity, right? And if you do that right and subtract it, then you will see that this thing, in this frame, where you're going with this speed, it will be standing still and rotating at a particular rate around it, which is just the rate of any of these, okay? Right? Huh? You know this, huh? Or not, huh? We can go through it, but we don't want to do this, huh? So let's analyze that now from a business perspective, okay? So what I'd like to say is, see, this rigid body, if it's a firm, if you are putting yourself in the body frame, so the frame attached to the center of mass, right? Huh? Okay, so that's the point of balance of the assets and the liabilities, okay? Then this thing has got no net movement, all right? So all you'll see is how much your net income and net outcome, huh? Now you say, well, I mean, why don't I see my profit? Well, what's happening is you're distributing your profits to your shareholders. So at the end of the term, the profit, you pay them out, and they're in the center of mass motion, right? That's the net earnings, okay? So then if you pay out the net earnings, your initial capital will just stay where it is. That's this thing, huh? You'll just have a feeling they're just turning, right? It's just your turnover, okay? So it's some sort of break-even turnover that you have. You're just running your business. I think that's where the name business comes from, you know? Huh? So there's a joke, like this guy, and he's taking eggs, and he's explaining his business. He says, well, I buy eggs for $1, and then I boil them, and then I sell them for $1. So he says, what? What are you doing, right? What's this you have? I said, well, what's the point of that? Well, he says, first of all, I'm in business. Oh, he is in business, right? He's not making any money, but he's in business. And second of all, I've got egg soup here, you know, which is just a one of it. Huh? You know, so he has nothing else to show for it because, huh? But anyway, I would say this guy feels he's in business. He's not making any money. Maybe he has a salary and it's some liability or something that gets booked, huh? An expense, huh? All right, huh? But the investors get all the net earnings, okay? So the net earnings, you just add up all the investor frame or spatial frame velocities, and you get the net velocity, center of mass velocity. That's going to be your net earnings. So that's the income minus the expenses, okay? All right, huh? And then you have this turning motion left over, and that's just your break-even turnover after you've distributed all the net earnings, okay? And that's just your angular velocity, all right? So all movements, and that's the perspective of management, right? So management is not making any money themselves, no, you know, unless they're the owner, right? Huh? They're getting a salary, sure, but that's different. That's an expense, huh? Okay, that's not a distribution. There's not a dividend or huh? Okay. And then what is the group that does this? Well, first of all, there is this rotation here. I said SO2, but this is not SO2, but this is the shear group. It doesn't matter, right? And you got the group of translations in two space, right? Both of them. This is when the investor would do a capital injection. You know, he may just move it over here, right? Or maybe when some of these earnings get retained, then you put it back and you put it into equity. I don't know. There are all kinds of mechanisms to move to the right. Huh? Okay? Huh? You would take some of these earnings not distributed, put it in retained earnings, but then it wouldn't be initial capital. It would be total capital. Huh? All right? So different ways. Huh? Okay? And this thing is called the Euclidean group. Why? Because they're all the motions of Euclidean space. So if I take this phone here, then I can move it like this, I can move it like this, and I can rotate it, right? I'm forgetting about this dimension here, all right? Huh? Talking to the camera, all right? Okay. This is called an indirect product because it's not a question, they don't commute, you know? It's not like a direct product of R and R where you can do this or that or this or that. you know, they kind of weirdly interact. If you rotate and then translate, or translate and rotate, there is some kind of strange interaction between these two that you've all figured out one day, or some questions on your werkcollege or homeworks, okay? Huh? And this is a symbol they use. It's called the indirect product of these two groups. Okay? So businesses, you know, when they're making no money, or if they're just from the point of view of the management, huh? You can just see it as rotating around a fixed point. From the point of view of an investor, huh? The owner of the business, you would have a separate frame. Huh? That's the inertial frame. And this is the center of mass frame, huh? The body frame. Okay? When you do robotics and when you have airplanes, I guess, it's always the same thing, right? So you are on Earth, you have your center of mass, spatial frame. Huh?
We have like 4 of them. There's that one that's in the middle of the Earth but doesn't rotate. One that's in the middle
rotate, yeah.
on the surface of whatever.
Yeah, I get it, yeah. You have 4 of
But
them.
you're right.
Yeah. Yeah, so you could use that if you have an ownership structure that is more complicated, right? So this, and then somebody else owns this guy, and then, you can have various frames, That's right. So corporations that's a corporation, right? So a business, you know, is just something that has balancing assets and liabilities. But a corporation, that means it's a legal entity that can have earnings, and the earnings go to the owners. And the owners and management are different. This is an important thing to see. So management is operating in the body frame, and the owners operate in the inertial or the spatial frame. Okay? And they're separate in the business, because the business itself is a legal entity which has, in our geometric language, its own frame. Okay? All right? Clear? So you see, this gets complicated pretty quick, but that's not a real problem. That's what it does in mechanical engineering as well. I mean, Andre is talking about 27 frames they use for, well, not that many. I think it was 5 or 6. What did you say? Huh?
I think 4.
4.
Maybe 3. Let's be
Maybe
honest.
3, to be honest. Huh?
Yeah. I haven't worked with any other than the body one for a long time, but I know they exist.
Yeah, so here you can have management, then you can have the, the investor, but then you can have a fund of, so mutual fund where they throw them all together, and from their perspective, they look at it again differently, right? Huh? Maybe they attach themselves to the S&P 500, and they feel that's the inertial state. So you can have 3 frames as well, depending on what everybody is comfortable with, Okay? But this group gets huge if you have 3 frames in it. You gotta, even as a metric, I mean, but it's just not worthwhile, determining what it is, or complicated matrix. And the exponential function is also, you can write it down, but it's just a big matrix, because they get these also homogeneous matrices, right? So they'll have here the element of SO2 here, and then they'll put this vector here, V1, V2, and I think they put a 1 here, or put a bunch of zeros here, right? And then you can describe this as a matrix. And then you can take the matrix exponential of this thing, so this will be a little SO2, some kind of, whatever. That's not what this course is about, these lectures are about. It's more to understand how you take an economic situation. Now, this is something economists don't deal with. This is more of a business analysis, right? I don't think they talk net earnings and things like that. But we want to take this more general approach. This is more of a business, but again, you can put it into geometry. And then immediately the tools are available in 3 frames to deal with this, okay? Now in practice, you probably make lots of simplifications, like we do, but that's okay, Huh? Gotta start thinking like this. Think geometrically in these things. All of a sudden, I find that as soon as I see this, the whole business of a business is not so complicated anymore. It's just okay. It simplifies things rather than complicates it. I'm sure a business person would disagree, but, but we're engineers. Okay? That brings me to my last slide. And then I promise next week we'll go and this one I ended up just not, running out of time before running off to this lecture. So it's a little bit less complete than the other ones. And maybe I want to keep it this way because things get pretty hairy and it's too easy to get involved with all the nitty-gritty of the math. So all the previous examples were mostly commutative. I think SE2, the special Euclidean product is not because it depends a little bit. And this is a really cool one in terms of non-commutativity. This is kind of the thing that lies at the heart of Lie theory, I would think. And it's called SO3. So you know what SO2 is now? Special orthogonal group. There's other rotations in the plane, right? There's our circles, okay? So in a plane, so you have two goods, eggs and chickens or something. If you amortize those, you get a one-dimensional submanifold, right? So one dimension of rotations. What if you have three goods? Oh yeah, and then let me say something else. But suppose you have this one-dimensional thing. So here you are. Here's that one-dimensional thing. So you're making these eggs. Now, how do you plot it when you do this over time? Well, you need this extra dimension. That's kind of funny, isn't it? Like what happens here? If you look at this amortizing behavior, you get these eggs. But a little later, these eggs go like that, and they go like that, right? So it's not really possible to imagine this thing staying in one dimension, right? What you want to do is add another dimension. You're really interested in the eggs, right? So they're going in the imaginary direction, right? So you imagine having a little rope, you put it here, just with the imaginary action. And what you're really doing is you're wrapping that around here, around that circle, and that's how you amortize, okay? So, but if you moment you do that, you need this extra dimension, right? So you need this real axis here. It comes out of nowhere in order to be able to describe what happens in longer periods. In the short period, you're okay. You just go here, right? But in a longer period, you need to know how much you're, okay? So that's something to keep in mind, that you need at least one real dimension for every, now product that you make, okay? All right. Okay, now let's go back to this more complicated situation, all right? So now, let's first do the, so we have now three things. So not only chicken and, well, I kind of screwed up here because I don't like what I did here because this was my real dimension and now I made it an imaginary dimension. So call this chicken meat or something, Okay, so I have these chickens, they're real chickens, So the word for the meat of a chicken and chickens is the same. Otherwise I would have pigs and pork, It would have been better, Okay? So these are, what do you call chicken legs, Chicken wings. Let's call this chicken wings. You see? So I have three products. So I have these eggs. I can also get some money, sell them for money. All right? And chicken wings. I just have three products. I don't even like this anymore. Okay? I just have three products I can make with my chickens. So the chicken wings, chicken legs, and eggs, or cows. I can have veal, I can have milk, and I can have cheese or something. I don't know. Just think of three products. I'm going to revisit this slide. There's three products, okay? So Okay, well, how many, with one product I have one imaginary axis, right? Huh? So 3 products, I need 3 imaginary axes, right? Huh? Okay? Okay, so here they are. I, J, and K. Now, why do I need 3 products? Why can't I do 2 products? All right? The problem is that if I have 3 different ways to rotate, 2 different ways to rotate, it doesn't work. Okay? Because here's what happens. So think of a rotation. So in the plane, yes, you can rotate only one. There's only one dimension, so you just need this one I-axis. But now you take one direction more, okay? And you're in 3 space. So what's going to happen? Well, you can rotate not in 2 directions, but you can rotate in 3 directions because there are 3 different planes you can choose, okay? You can take the IJ plane, you can take the IK plane, and you can take the KJ plane, right? Huh? You see? Is that right? Okay, whatever. I'm missing it up a little bit, but we all know that in 2 dimensions you can rotate one way, in 3 dimensions you can take, I'm messing this up a little bit because it's not these planes that matter, but there's 3 ways to do it. This is a problem, okay? So these 3 ways to do it is just a frame like this. These are the 3. I see that I'm not. I'm gonna wing this one, and then next time we'll clean it up. All right. So let's just wing this one. Maybe we'll get it out of the recording. Well, I still have a little bit of time. And here's the idea. So this is. Hey, Ahmed, you can throw this off the. We're just gonna talk about this. Okay. So here's the problem. So what do I do in 3 dimensions? So in 3 dimensions, I have 3 possibilities to produce. Okay, that's true. Right? So I have 3 dimensions. So here were my old dimensions. This is the ambient space. Before I will have only this plane here. Okay, but now I can use this plane, and I can use this plane. Right? So all of a sudden, my business can do 3 things. I can exchange chickens for money, I can exchange chickens for eggs, but I can also trade money for eggs, okay? Now I'm doing a better job, all right? I know exactly where I got myself messed up, and this is just I should really put little hats on here, so whatever, You see? That's the problem, So, you see, by adding one more good, by adding chicken money to this thing, we get 3 possibilities, okay? 3 planes. Now these planes are indexed by an imaginary number. This is what's going on, and this is confusing because in SO2 we use the imaginary number for the tangent, not for the plane, but it should really be the axis coming out, okay? So these imaginary numbers are a little bit different, and they're vectors that are orthogonal to the plane around which you're going. So sometimes that's indicated with a little hat here. Okay? All right? So this is where I got myself confused. Okay? Are you following this? So we can imagine every plane will have one imaginary number that we're wrapping around, but the other way of wrapping around is to put an axis and then count, if you have a screw, count how far you go along that axis, as it were, right? And there's just 3 ways of doing that, okay? Those are the I, J, and Ks, okay? Now we assume that all of them are amortizing. So all of them squared are going to lead to -1, right? A loss of chickens, okay? Or something, okay? Right. Then there's something else going on, is that if I first rotate in this plane and then in this plane, I'm going to get effectively a rotation in that plane. So if I first let chickens lay eggs and then sell the eggs for money, I get a direct trade of chickens to money. You see that? Huh? So here's chickens, here's money, here's the eggs. I can go like first create these eggs and then do money, or I can immediately just sell these chickens to somebody, let him deal with the egg and sell those eggs for money, right? Huh? So if I do I times j, I'm going to get k. So a trade, one trade or one production followed by a sale is immediately a sale, okay? All right, and you can work your way through the other ones, okay? You see that? You're not seeing, are you seeing that? Huh?
Yeah, I'm just thinking about the K, I, J. So if you first get the money and then the X, it's the same as.
Yeah,
K.
of course it is. Huh? It's all symmetric anyway. Huh? You see, I can turn this thing, I can relabel it and you'll see that it's right. Huh? And if I do it the other way around, so J and then I, I'll get minus K here. Okay? Huh? That's clear too. All right? So there you are. This is another nice system. All right? Now, if you look at this, you'll realize that it's really not possible if you have money, chicken, and eggs to pretend you don't have money. Okay? Because as soon as you do one axis, that you can't do the other trade effectively. You see? Because if you do this and that, you're not going to end up to 1 or J or I. You end up in something else. K. All right? Huh? So if you have 3 dimensions, you got to have 3 of these. Huh? But that complex number is going to have 4 coordinates because there's still going to be the real thing over there, right? So you still have this counts the chickens, and these count the different types of businesses you can do. This was Hamilton's problem. I don't know if you've heard the story, that people were looking for complex numbers. So you have this complex numbers, this, and they thought they could just add CJ, now. But it didn't work. And they couldn't figure it out. And the reason is that you have to see that I times j is equal to k. So you need another one. And then it will be okay. Then the system is closed. If you start multiplying, and multiplying means doing one action after the other. For first this trade, then that trade, then you're going to have to add this as a possible trade. Okay? All right? Okay? So, it's also said that this measures how non-commutative it is, right? So by doing things the other way around, you just, okay, So you see this more often with non-commutative things. So parking your car is also a great example. Is a car can only go forward and you can steer. So how do you go sideways? How the heck? You can't, right? Yes, you can. You can parallel park. So you can go sideways. But what you got to do is you got to first steer and then drive and then steer back and drive back and you go, and then if you do that infinitesimally small, you're going to go sideways. Okay? So you see, if you look at the closure of this kind of stuff, you're going to end up in a larger space. You have no choice because the car can go sideways. You don't know. Can make all kinds of things. So, so you gotta. That's the same thing with this business. If you're willing to sell your eggs and you're willing to let your chicken create eggs, you basically are capable of turning chicken into money, and you can't pretend that you can't. That's what this is saying. All right. And that was Hamilton's problem. So you see it out in 3 dimensions. It works. But you need a 4-dimensional space to do that because you still need that real axis, that you need when you go integrate out. Okay? All right? So whereas before we would just have this I-axis as saying, okay, what's an infinitesimal amount of amortizing? Now we have 3 of them. So we have a bigger space. We have a 3-dimensional space, where we have a 3-dimensional vector space which have the angular velocities on it, okay? Now that 3-dimensional space can be embedded in a 4-dimensional space, just like that 1-dimensional space could be embedded into 2 space. Okay? All right? And that space is called SO3. And you can picture it, and there are several famous ones. This is called the Hopf vibration. There's also called the Bloch sphere. That's what these guys at Quantum use for their qubits. Qubits also follow SO3, right? Huh? So what the Bloch sphere is, it's like a regular sphere. So this is S2, right? Huh? But it doesn't. We need S3, right? A sphere in 4 dimensions. Okay. So what you have to imagine is that every point on the sphere there's another little circle. Okay. So to do a rotation, you give the axis of rotation. That's this thing on the sphere. And then you have to tell me how much you rotated around this axis. Okay? Okay? So you can create SO3 from a sphere and a circle, but they have to be enmeshed in some way. And this is what the guy did here. This is Miles Johnson or somebody. So he looks at different axes of rotation, and for each axis he finds a circle, and then he meshes them together like that, right? And then you get these kind of shapes. And this is called the Hopf vibration. It's called a vibration because for every axis of rotation you have a fiber that is a circle. There belongs a fiber at that place, okay? And that's the way this thing looks. Super complicated. You know what's great? Any point, you can just take out, this thing is, this is the Lie algebra. So these are the rates at which you're going. You're doing a small cell, this one you can understand. If you just take the exponential map, boink, you're in the right place. All right? So in the end, it's the same story as this one. Huh? Look, this thing you can understand, a little bit of production or this one, and then you take the exponential map and you just, you take the right thing. Huh? And you get a circle and you go like, oh, huh? How's that? Okay. Huh? You can still do it because your circle is in a 2-dimensional space. It's easy to visualize. Unfortunately, this Bloch sphere over this Hopf fiber, this SO3 is in a 4-dimensional space. So you have to visualize it in some other way. The cool way is to just look at this and take the exponential map. That's what everybody does. Angular velocities, 3x3 matrix, take the exponent, huh? And you're done. Again, this is a business, huh? So it's a business that where you also run money, and the money is amortizing. And this is probably not a very good example because money doesn't amortize like that, but whatever. You can do the same for SO3. You can do for hyperbolas. You can do the same for kind of cylinders and that kind of stuff. Gets a little easier, huh? So you choose whatever you want to fit the economic situation. Huh? These things get very hairy, but
Money does amortize, right? It's inflation. Like money gets less value. You can buy less chickens.
Yeah, but it doesn't amortize in the chicken space, right? You see, huh?
Yeah. You put it like that.
No, but that's what I meant,
Yeah,
right?
yeah,
So.
yeah.
These chickens are not dying, huh?
No.
Maybe because. So you got to add chicken meat. Is probably the better one,
yeah.
right? Huh? Huh? And then these eggs turn into chicken, which you sell as chicken meat, huh? So something's got to die in that space, right? Because otherwise you don't go back, right? I mean, you can combine amortizing thing with compounding thing, and then you get hyperbolic. You'll get a different group. You get SO2-1 if you have 2 circles, and otherwise you get SO1-2. They're all different groups, okay? So, So as you can see, I did a little bit of a shoddy job here the last time and this time again, but the idea should be clear, huh? So I'll clean it up for next time a little bit so we'll go through it. But it's fun stuff. And then when we've done that, then we can move on to do some. It's surprisingly difficult to get this right, isn't it? Huh? But once it's right, you go like, okay, clear, huh? But huh?
Like the higher dimensions after 2 and 3, then it just becomes.
Yeah, it's a bear. Yeah. Right. Yeah. Yeah. I mean, to do that, you see, rigid body dynamics is a very important field, and it just happens in 4 dimensions. And that's only talking about the rotation part of it, because you also have so E3, huh, is R3, and the semi-direct product, I always forget which way, SO3. So this is 3 dimensions. This is 3. And they're intermixed into a 6-dimensional space, right? That's hard. But yet, this thing is, somehow we can process it. And, this is what you need to do all the time, right? So, huh? But the math is hard. It took them a long time. And they're still working on this problem, how to really solve this. Huh? It's a difficult problem to do it right. There's some tricks, and then you'll see that it doesn't really work. You get this thing called gimbal lock. Then you have to use quaternions, and you don't get gimbal lock, and they don't really know why, and then they figured out why, and then what are the equations in Euler's the body coordinates? That's Euler's theorem, and then the regular spatial. What is momentum in these different frames? It's all very hairy, huh? Yeah, very hairy. And yet, it's there all the time, right? Huh? So, but most of these problems are solved without looking in these spaces. And then it is even harder, because don't forget, they spent hundreds of years kind of trying to get it right, and then all trial and error. Huh? Now finally get some equations that sometimes work, but sometimes don't. And it's recently, I think, I think Arnold started it maybe 30 years ago, well, maybe longer now. He started looking at it from a group theoretic point of view, and that kind of cleaned up a lot of it, You just had lots of equations. So, yeah, but it's right. It's hard to imagine. It's also hard to imagine spaces that are not Euclidean, You always put in this Euclidean metric. So.
It took them 2,000 years, right? To
Yeah.
have
It took them, yeah.
something like that.
Yeah, 2,000 years to realize that not everything is Euclidean. Huh? They really, they kept thinking that parallel lines should never meet. Huh? That was an axiom, but they felt it shouldn't have to be, right? Huh? And now we know that in the projective plane they do meet. They do. And then on the sphere they also meet. They meet twice, right? So lines on the spheres are great circles, and they intersect at 2 points. Okay? You can't have a great circle not intersecting another great circle, right? Huh? So this is a geometry where every line intersects at 2 places. The projective plane is a geometry where every set of lines intersects at 1 point. It could be that the point is on the horizon, but they always intersect. Parallel lines, the point will be the horizon. Non-parallel, they're not on the horizon. That's the only difference. Okay? And then in the hyperbolic plane, you have many parallel lines that never intersect. Never, ever. Huh? They're called ultra-parallel. Huh? So it took a long time to throw away the parallel lines axiom, So it's just the evolution. There's a nice book by Langsels about this, the evolution of the concept of space, how it starts off with Euclidean space, and then starts evolving into state spaces or this spaces or that spaces. And now mathematics has got spaces, they've got L2. This is a space of functions, infinite dimensions, Hilbert space. That's Hilbert space, I guess. Huh? So this is even harder to imagine, and yet it isn't, right? Because if you do a Fourier transform, there really is distance in Hilbert space. Huh? So, yeah, so there's a development of the concept of space that occurred, especially in the 20th century, starting in the 19th century, and then going crazy in the 20th century. So control theory is all about this crazy spaces that were in state space, state space models. Complex plane was the beginning, and it's also a different kind of space. Huh? With points at infinity, like the pole, what is it? These pole, the pole, how do you call this? The plane where you draw the poles. This is the S-plane. Huh? The S-plane has got one point at infinity. You know that? Huh? You know how you draw these poles? Huh? You have a pole here, and then they flow off to infinity. Huh?
Yes.
Yeah?
But I suppose they can also go the other way, right?
Yeah, but they go at the same point at infinity. There's only one point at infinity. They don't have a line at infinity. Huh? Yeah. It's called the point at infinity.
But if you have like a Nyquist plot, and
Yeah, when you go around the whole half plane,
Exactly.
you come back the other way.
Yeah.
That thing.
Yeah, that's what happens.
Okay.
No, that's what happens. You know how to picture those things? You know how to make sense out of that? It's really easy, yeah. So what you do?
Just like air.
Yeah. So this is your imaginary axis, this is your real axis, right? Huh? And then you put a sphere on this, okay? So this is the equator, you call this the equator. And then I'll just draw a sphere, right, like this. Huh? You see that? Here's the South Pole. All right? Huh? Okay. And then I call this the North Pole, and I'll call that the point at infinity. All right? Okay? I have a little light here. Then I'll take here a point, say, on the real axis, the negative real axis, and I'll draw a line between that North Pole and that point, and I'll plot it right here. So I'll take every point in the S-plane, and I project it right up to the sphere. Okay? Can you see that? Huh? So the equator just stays where it is, right? Everything underneath the equator gets plotted there, huh? And everything above gets plotted out there, all right? Now what happens if you move off this way, right? Well, so where's that point? All the way there. No way, it's just the North Pole, right? Huh? So you see the point starts traveling up along the meridian, huh? And it hits the North Pole, right? Do you see that or not? Huh? But now suppose I travel this way, all right? So I start here, then I go there, huh? Here. Yeah, also hit the North Pole. So I can just fly through the North Pole, and I move, and I emerge over there.
Yeah.
Huh? It's like a lighthouse projecting on the shore. So it's going like this, and it flops out, and then it comes back over there as the light turns.
Yeah.
Huh? So maybe this is the wrong way to look at it. This is what happens. These poles are on a sphere. So then you can see why these are conjugates, and why this one is closer, because you're projecting from the southern hemisphere here, so you're going to get close to zero for the conjugate, and infinity is over there, right? Huh? And all of a sudden, it's not so magical anymore that you're flipping off to infinity and emerging at the other side, is it? Huh? You just made, this is a stereographic map of the Earth. That's what happens. If you make a stereographic map, you go on that edge, you emerge there. Why? Not because you flipped through infinity, it's just because you went through the North Pole. Huh? The guy living on the Earth, he didn't feel anything funny. Huh? He just went to the North Pole. He's saying, why are you so confused? Huh? Yeah. But this is a flatlander. He lives in a flat space. He just sees these shadows. He lives in this theory. So this is a chuck, and there comes over there. You know, what's happening? Huh? You know? Huh? Oh, the Earth is round. You know? So you sail with your ship out, and you come in on the other side. You know what? He went off to infinity, and then he came back, Columbus. You know? Huh? Well, it wasn't Columbus. It was Magellan, I guess, who was the first one to do it. So what do? Well, you just say, oh, I suppose the Earth is round, and it's our map that was a problem. Huh? The map is really not a problem either, as long as you identify all the points. You see, if you go to this point, you also end up at the North Pole. So this complex plane is different than the complex plane we had. Then we had a whole line at infinity with an horizon. That was a flat one. This is the complex plane plus one point at infinity, you know? Because you take the whole complex plane and you take the edge and you just glue them all together, and then you create a circle like that. Huh? Okay? Now imagine yourself living in three space and looking at a four-dimensional thing. And things can shoot off and come back, but really they're happening in 4 dimensions, on a sphere in 4 dimensions. You know? Okay? Huh? So, huh? Okay? Anyway, huh?
Cool.
Yeah, it's cool, no? Huh?
Dit is ook in Dutch geestverruimende middelen. Vind ik, dit is wel geestverruimend.
Geestverruimend, ja. Mind expanding.
Ja, mind expanding.
Yeah.
Yeah.
Enlightening. Huh? Yeah, it is. You just make everything, all of a sudden everything becomes easy, right? Huh? Yeah. So the pole plane is in fact a sphere. Except they teach it to you like as if it's a plane. So it's the same as people who didn't realize the Earth was round. They have to teach all this chunk. You know?
Also why they call it poles? Because of the North Pole.
Yeah, sure. Right, yeah. Yeah, so yeah, the early guys, they knew what they were doing. They realized this is the Riemann sphere, it's called the Riemann sphere, and it's another projective space, right? So you project out from, now from the North Pole of a sphere. It's just we have the real projective plane. That's called the complex projective plane. Okay? Complex projective line, actually, because a plane is a line in complex geometry. So a line, if you look at a line, it has only one point at infinity. A plane will have a line at infinity, and a line have a single point at infinity. Okay? So the complex plane can be thought of as a complex line, a projective complex line. All right, you check. You know, huh? Okay. So it's called CP1, I think. We have RP2, real projective 2 spaces, and CP1 is complex projective line. That's the pole plane, and there's a couple of other things, right? Huh? I have to put it on this thing on pause. Huh?
They're getting a whole additional lecture.
Yeah.